some theoretic support. So I guess here actually the algorithms and the tools are more important than the technical details. If you have any questions, please just ask them. Okay? So,
hi everyone, my name is Pranav, and today Wenhao and I will be presenting a presentation on PAC learning and complexity bounds. So in this presentation, first we'll try to describe the problem of learning framework, and then we'll define the PAC learning framework and use an example to illustrate it. And after that, we'll introduce the idea of learning bounds and for finite hypothesis sets. And from learning bounds, we'll introduce the idea of complexity bounds. And for in order to describe the complexity bounds, we'll give show some applications and examples. And then we'll describe metric entropy, and then we'll show some example to describe. Alright, so for a learning algorithm, there are a few questions that are to be kept in mind when we are constructing an algorithm. So the first one is suppose we have a set of examples, per se, so this is suppose a set of examples, and from them we are mapping to a set of target values, how should I put it, we are using a concept on these set of examples to learn the target values. So this is essentially a mapping from x, x to y, and so the first question that should be asked is how many samples that we need to draw from this set so that we can get a successful hypothesis that would learn this unknown concept. So that is the first one, and the second one is the computational complexity. So it's how much computational cost we can spend on an algorithm to find the successful hypothesis. And then the idea is we don't know these concepts, right? But we are learning it through the examples and the target values. We are using them to learn these concepts via one hypothesis, right? So the hypotheses are supposedly not exact to this concept, but they are approximating this concept as good as possible. So in this case, how many training examples we need to have as minimum misclassification as possible. All right. So these are the questions that are need to be answered in order to find a successful learning algorithm. So these are the notations that we'll be using throughout the presentation. So this is the x is set of all possible examples and y is a set of all possible labels or target values. So this is the unknown concept that maps from x to y, and for given x it provides a value from y. So in this presentation we'll mainly focus on the classification problem. So the y set is like a binary set of 0 and 1, and so this is the class of concepts which is denoted by capital C. And so this S is the sample that are drawn from this script X. So it's a sample of size M, and it has an unknown inherent distribution, probability distribution D, and we are using this hypothesis H to learn this C, and this is the class of hypothesis is capital H. and like the usual the definition of like we use L as the loss function, and this G function is it maps from the cross product of x and y to the like the set of loss function like to the should I put it like the loss functions, right? So all right.
Just a notation mark. I understand. So, can you give me some examples? I mean, it's some abstract words in jargons, but you can make a connection to maybe a real world problem.
Yeah, I will go like make everything into like a.
Could you explain a little bit here, because some people may not be familiar with this abstract notation. For example, X could be.
So X could
sample
be
space, right?
Yeah, sample space.
And Y could be.
Y could be the set of dependent values for
It's just a classification problem.
Yeah, for classification it's like
So
0
it's
and 1.
binary, right?
Yeah.
And what do you see?
So the C is a so it's like the classification is the function C.
Classifier.
Yeah, the classifier, yes.
Right, with the right parameter.
Yeah.
I mean, you should give such intuition when you teach a class. Right? And L is the loss function, is like our, maybe like a negative log likelihood. It's like that.
Yeah.
Usually we don't want to use it because we don't want to assume some, essentially it's done in an unparametric way. You guys should see it. So you can make your maybe Bernoulli assumption, but here maybe you want to go beyond that. So L is my loss function. It may not be a negative log likelihood function, but if the ideal case 0, 1, maybe in your case, you just set it by 1, right? And G, what is G, little g and big G?
So so the G function is like it maps from like the cross product of x and y to the set of loss functions, like so
I don't want you to read the notation, just give some examples.
Mhm.
These guys need to understand.
so I guess for example it's
I mean, why there's a family, right? That's the key one.
yeah
Okay, move on. Maybe you didn't have a chance to explain this thing. But basically, everybody is clear of that. I mean, essentially. Okay.
So in this like learning framework, the two measures that are really important. The first one is the risk, and the second one is the empirical risk. So the risk of this generalization error is something like so it's we all know like what like a risk function is like. It's like so when we have a misclassification, so how should I put it? It's okay. So the idea is suppose we have a classification problem where so suppose this is like the class of examples, which is like divided into two parts, where like one part is classified to like one part maps to 0 and another another part maps to 1, right? So when we're trying to learn this setup, we are going to use another mapping, another like function hypothesis, for which we might have some case misclassified, right? We'll have some case misclassified. So under the underlying distribution D, the probability of like the total misclassification is the risk, right? But when we have a sample, we calculate the empirical risk from the sample as using the indicator function. Like when for each sample, if it's misclassified, it adds 1. If it's not, then it adds 0. So this is like the usual risk function, and this is the empirical version of that risk function. Alright. So
What do you have training data?
For like the training data is this S, right? So from this we calculate the empirical risk.
I hope you guys understand. Well, he said given any hypothesis, so H is given, but you know actually H can be learned, right? But anyway, if you don't talk about H, it's basically like you're like evaluating a test error using like 100 observations or using population version. It's not only that, Renee, it's not only that, right? You also have to talk about this H in some sense. I mean, here right now, it's just like empirical, the law of large numbers, nothing else. But we actually care about the overfitting issues or the other related issues. So you can give a better explanation. Yeah, the first time here, so maybe you didn't really see how we question people. Well, you have to give a clear setup by maybe providing more examples. I think this is okay, but if you want people to understand you have to give examples. Not only just some abstract setup and notation. So, this is not really a difficult thing to understand. I don't know why it took so much time to organize this thing. I think he probably understood. So the generalization error, everybody knows, right? We care about the generalizability of that learning algorithm. So we truly care about, in statistics, we care about like the prediction error, test error. But the test error, prediction error can be evaluated on a subset, on just maybe a data set, test data set, right? Still, it's better to have two separate data sets, one for training, the other for test. But if you really want to calculate the test error, it should be based on the expectation. That's going to be more accurate. But you have a large enough test data set, that should be fine. But the point is not only here. Actually, the point is, if you do learning, you have to minimize some criteria. Should you minimize the empirical error? Yes, you should, but it's not enough, right? Because this sample, this small, set of examples may not be representative of the overall population. So this actually has only limited sense. Especially when the number of samples is smaller, then we shouldn't really pay too much attention to the loss. Instead, actually, we should do a combined criteria. We need to add regularization. We need to, that actually can connect to your later knowledge point. Okay, there's a book. If you have time, you can read it. It's called Foundations of Statistical Learning Theory, or maybe Statistical Learning Theory. There are two versions. One is actually to students, say in college, undergraduate students, or maybe master's student. There's another one, also with Daphne, it's actually much more advanced. It's very thin book. Like we call it 3 milestones of statistical learning theory. Okay, interesting. You have time, you can read it.
I have a question. So here, X is from the, so you assume like given the true label will be like deterministic on each X, right? Y is CX, which is deterministic, or it has some like error. Like for same X feature, the Y is determined or not in this setup.
For same X feature?
Yeah.
For same X, yes, for one X, like for a given X we have a Y, right?
So it's deterministic. You don't have.
If you keep having the same X, like repeated experiments, should I see exactly the same Y or a random Y?
Yes, for a specific concept, yes. You'll see the same.
What do you mean by yes? A random Y or non-random and deterministic Y? Do you have error there? And do you have noise there? That's a good question, right? From your slide, you didn't really say anything about it.
Yeah,
you understand?
Get it, like, so like for a specific classifier, right? We won't have any noise. Like like so for like a specific classifier, we'll always have like a sample will always like a value will always return the same, like the classification for that value, right? So
I don't think you got the question. Shaw was asking, if you have x given, then you have some y, right? C of x, actually. There's no y, actually. There's no y. There's a C of x. And then you will have another x, which is identical to a previous x. Should you see the same C of x?
yes,
Yes.
yes.
Do you understand? But why is this happening here? Do you understand, Shaw?
I don't know why it should be.
The rule is fixed.
Yes.
The rule, the C is fixed. For example, I can easily say, well, x greater than 0, I'm going to do the sine function. That's my y. But this is fixed. So basically, C of x is like, I mean, if you have x given, it's like your expectation of y. But the randomness, you can introduce still some randomness in x. I hope you guys understand. So if you have a GIM model, what is really the target of in the modeling, statistical modeling? Is it y? Expectation y, exactly. So if you know the expectation y, you can write down a loss function, and that's all. Here is the same thing. If you know the expectation function, you can write down a loss function. Do you understand? If you know the expectation y, then you build actually deterministic relationship in response to, I mean, the expectation y. I mean, of course, on the systematic component. So that's a fixed system. And then I use my, loss function.
Should I try to give an example?
Yeah, I mean, this is not the standard statistical setup because in regression, for now you understand the importance of this function, right?
Yeah.
What is the assumption in regression or in like binomial, logistic regression? We have x given conditional x. We have random y,
Yeah.
and then you use the distribution of y to give you the log, negative log y to construct a loss function. So y is random conditional y, x. But the setup here is a little bit different, right? But if you care about the expectation of y, then it's actually a deterministic relation. I mean, GLM. I hope you know what I'm talking about. You should be while explaining this. Okay, so C of x is fixed. C of x
Yeah,
is
so
fixed.
like, suppose like we for like we have x belongs to like script x, and then it's like suppose in this case it's our d-dimensional space, right? And we define the class of concepts as let's say like C of x is less than like C of x. It's 0 if norm of x is less than some value. So depending on the value, the concept changes, right? So that's how we're classifying the d-dimensional Euclidean space, right? So in this case, a specific C is given for a specific value.
Parameter there.
Yes.
And then I have a capital C.
Yes.
Then you can see the problem is separable. I mean, right now. I mean, it's still a reason. I'm just saying it's still a reasonable setup. But later, I guess you will have actually more. But this is actually something you should see. Compatible. To what you have learned in some sense. But there is no y error. Okay, you have to point out explicitly because in statistical modeling, you have to assume there is another level of observation noise, something like that. Right. So it's like a separable case.
So the idea of the PAC learning framework is
By the way, easier to call PAC.
okay. So of an algorithm is say PAC learnable algorithm if we have this condition satisfied. So I am going to explain this condition. So the idea is suppose we are given an algorithm like script A. So if this algorithm So if for this algorithm we have an m satisfying this like m, like for any m greater than a polynomial function with like these values. So for any given epsilon, even given delta, and like the dimension of the example class, and like the size of the concept. If we have like the sample size greater than this thing, then the risk is bounded with very high probability. So if it's true for any m greater than this value, then we have then we say that the algorithm is PAC learnable. So PAC stands for probably approximately correct. So I'm going to explain this with an example. Yeah. So,
I mean, this is important. Can you explain more? Which are given and it is parametric or non-parametric in the statistical sense? In polynomial, what does it mean?
so but
I mean, people should ask you questions on that. Because to most of you guys here probably this is the first time, right? Have you, I mean, any of you actually have learned this PAC learning framework?
Yes, was learning class of Dr. Bambus.
Yeah. Okay, very good. But did you show anything in theory? Or just introducing the framework? Okay. You can use such things to prove some, bounds for lasso, random forest, all these things. I hope you can still actually explain this a little bit more.
yeah, I'll explain it like through the example.
Okay, what's the intuition? Can you use one sentence to summarize this thing?
So the objective is to find an algorithm for which if we have the sample size at least like more than a minimum like threshold sample size, then the risk of that the risk of the hypothesis corresponding to the algorithm is bounded with high probability.
Which are the important parameters? Epsilon delta and all, right? I mean, it's not epsilon delta, right?
No.
Yeah, I really wish you could make connection to something you have learned.
First, n is the size of samples. X is n the size of
dimension
x or
Yes, see?
of
I mean,
x.
Renee, you should really explain this thing. What is really N, MC, I mean, all these things. You have to see the problems. What are important parameters? There are so many parameters. I mean, maybe you don't have to take time to explain each, but at least tell me which are the important ones.
So the main thing is like the sample size.
Okay, so that's M.
Yeah.
Okay, so
And-
that's important. That's very important. You have central limit theorems. You have learned that. I mean, n goes to infinity. The problem dimension is fixed. We should see something good. Yes, n should be large.
Yeah.
Right. How large?
As less large as possible. That's
Yeah, I mean, how large? Explain the poly.
Oh, so like the polynomial function will be like
Let's forget about the epsilon delta. So polynomial in.
so
Check that.
yeah, so it's a polynomial in so like the dimension of the script x,
What is that notation?
that's n.
But x is a set. What do you mean by the dimension? Cardinality?
Like yeah, cardinality. Sorry, yeah, sorry, yeah, cardinality.
If you use an example, that could be much easier. So for example, you have features, you have non-parametric things. I mean, I really wish you could give an example. So M is the sample size. What is N?
And
What is N?
so n
Yes.
is the like the cardinality of like this set.
I don't know what this set means. I don't understand. This set, that set, I have no idea.
Can you give an example of a PAC learnable thing?
Yeah, I'm giving.
But what is X? I mean, you can't say this is X. This is nothing, just notation. I can call it Y even.
Yeah, it's.
What is N? Still, what is N?
Um,
Use your words to explain it.
it's the like the cardinality of the collection of independent variables.
Independent variables. Okay, so that actually is related to so just the number of what? If you have a reversional classification setting, what is n here?
It's the number of like the parameters.
Yeah, I mean in some sense, but you could consider a non-parametric model. It's actually the number of variables, independent variables. If you think of this as a function, then it's an independent variable. But it's random. Don't forget, you assume they're random. So it's not a good way to call them, I think, in some sense, independent variables. You can think of this as number of features. Yeah. I mean, why not say, you have to convey the message per name. We don't really know what X is. Okay, then what is size of C?
So the size of C is like the cardinality of the concept class.
Give me an example.
So suppose
Okay, let me give you a setup. I mean, but you have to think about this, Pranay. It's just not just some abstract thing. It's very much related to the class you're learning, to the topic you're doing. So for example, I have a sparse setup. I have P as my, actually N, number of features. And I have sparsity, right? So what is my size of C?
so the size of C is like the number of non-zero variables.
It's like that, but you have to say this clearly. You have to make your assumption and then state it. You have a sparse setup. How do you formulate this problem using your C, N, M?
So
Okay, we don't have time. Let's say we have N samples, P features, and then we have sparsity. What does it mean? Maybe the number of relevant features is less than or equal to, say, 10, or maybe N over 10, who knows? But it's 10. Then, how many concepts do you have?
sorry.
Okay, we have N samples, P features. We want to do classification, or maybe just not so. I mean, just variable selection. You have various algorithms as a learning algorithm. But what I'm saying is, what is really the role or the meaning of C? You have to give these people an idea. And what I said is, let's assume sparsity. Then you need to add assumption. Sparsity, what does it mean? I give you another assumption. For example, let's say the model size is less than or equal to 10. If you like, you can put it like 1/2 of N, but it's the same thing. Then what is the size of C?
So
Just linear model. You don't have to consider nonlinear effects.
yeah, so in this case the size of C is like is P, right?
Not P, not P. P is the number of features. This concept is related to your assumption. This is really what I want to point out. You may have like 1 million features, but you have to add in some structural assumptions. What is my structural assumption here? Sparsity. And maybe actually even more explicit. I said maybe I have only 10 relevant features. Then what is your, size of C? I think the size of C.
So then it's 10.
Like what?
10.
10?
1 million choose 10.
Yeah.
Oh.
Exactly.
Yeah.
You have to see the connections. You didn't even think about it. You just thought, oh, this is some general framework. But what is really the role of these parameters? You didn't even think about it. Sample size should be large, of course. And the dimensionality is bad, actually. We know, if dimensionality is smaller, then it's easier to handle. Otherwise, we have curves of dimensionality, right? Everybody knows that. And then size of C. What is size of C? This is very different than the original, if you know, the cardinality of your X. The cardinality of X doesn't really mean a thing even. So it's actually like your number of features. But size of C is related to your model. If I consider a non-parametric model, size of C can be changed. If I consider maybe just linear model with sparsity, it can also be changed. And that's why I think you listed in your I mean, like on this page, you have maybe like metric entropy that could come into play, right?